Okay, so just refresh what you have learned in the previous our lecture class during the previous lecture class. Okay, so introduce for you what is meaning by the blocking. This, in fact, the blocking you have learned it in the earlier than the last week. Okay, maybe the second week you have learned what is the concept of the blocking, and then after that I will introduce for you how is the confounding system. Okay, for the 2 power k factorial design. Okay, so the blocking ideas I have mentioned it completely here. Okay. Then after the blocking, I have mentioned it to you that how we want to run the confounding, because we are unable to run all the treatment combination within a block. So therefore, we let you run less. So the number of the treatment combination within the blocks will be the 2 power of p, where the p will be less than the k. K is referred to number of factors you have. Okay, the p is a form the less number of treatment combination. Okay, so for example, if you have a 2 power, you have a 2 power of 2 treatment combination. So therefore, you only can run is altogether is 2 factors. You have a 4 treatment combination is a 1 A B 2 power of 2. So we can be run for each block consists of the 2 treatment combination only. So therefore, here you run these 2 at the same block. This 2 is another block. These 2 at the same block. These 2 another block. This one is these 2 in the same block. These 2 is another block. Okay. Each block contains of the 2 treatment combination. So, but which are the combination you can choose? It depends on which are the information you're willing to give up. Because now you have a 2 power of 2 treatment combination. We will expect that all the information we can get it, all the information here. But the problem is if you're willing to run only the just the part of the treatment combination, so therefore you will lose certain information. Okay, so here I have mentioned it to you that if you're grouping the 1 and the A together in the same block, the AB in the other dot, you're using all the plus together, all the negative sign together. So if you do it in this way, this one we call as AB will confounded with the block. So how you want to know that is the AB confounded or dot? You just refer to the AB, the sign here. If the positive sign will group it together, negative sign will group it together, then we say that they are AB will confounded with the block. So if the AB will confounded with a block, means that the information for the AB, you can't obtain the information itself anymore, because the information from the AB is already confounded together with the blocks. Okay, so this one is the information we lost. You can't get the sum of square for the AB anymore, because this sum of square and this one block will be together. Okay. So under the testing of these 2 power of 2 factorial design, so we will lose the information of the AB, the iteration of the AB here. If you do the AB confound, if you use the AB confounded. Okay. So this one is what I have discussed you all. Okay, I have shown it to you how to do it. If another one, if you want to do the 1 and the B is negative and the A and the B here, so the A will confounded. So if you do the A will confounded, means that the or the effect of the A you can't get anymore, because the A factor of A here will be combined together with the block. Okay, so in that case you can't get the information for the A. But you must remember that A is your important factor. You want to study this experiment, A will be important. B also will important. You want to see that whether the A have a significant difference or the factor A will important. And then you're also interested about the factor B. Also, the factor B will important. Therefore, we don't choose the main factors, A or B, confounded with the block. If you do it in this way, then you will lose the information of the A. Okay? So this one is the idea of which one you should be confounded. Okay, so the practice will be we confounded has a higher order iteration, because the higher order is not the important, because if you have a many of the iteration, then we choose the higher order to give out this type of information. Show you the example how are you going to do it in the grouping where you do the confounding of the ABC. Okay, so the idea of the ABC confounded, I have shown it to you how to do that. Okay, so the confounded you can be do in the 2 blocks, or you can do it in the 4 blocks, and so on. Okay, so these are the example to you that if this is the example for 2 power of 4 factors, A, B, C, D, you have 4 factors. So suppose you have altogether is a 16 treatment combination. You have a 16 of the treatment combination, but you divided into the 2 parts. So the block 1, you run the 8, another block, you run another. Only run 8 treatment combination. This one is another 8 treatment combination. Okay. So in this case, because they use the following one, so they will do the ABCD will be confounded. Okay, they confounded the factor high order iteration, or the highest order iteration is the ABCD. So means that the information ABCD, you can't get the information here anymore. Okay, so this one is called that if you calculate the block effects here, if you from the block 1 to the block 2, you calculate the negative 18.625. Actually, this block effect is consists of the effect from the blocks and the ABCD. So they were together. Okay. So if you calculation of the sum of square for block, also the sum of square for block, this sum of square for block is actually the square together with the ABCD. Okay. So I have show you to you. Okay. If you do the confounding, okay, and then in the case 1, I have mentioned that if because you have your n is equal to 1 in this example, the n is equal to 1 for the case of the n equal to 1. Therefore, you do not have your sum of square for error. Okay, the first information you don't have the sum of square for error. The second you were lost is because you are doing the confounding of the ABCD, means that the sum of square for ABCD you also unable to get it. Okay, so you lost 2 information here. So if you want to under the sum n is equal to 1, the sum of square equal to 0, how you want to fix this problem? It can be group all the high order iteration together. Means that we willing to give out 3 factor iteration were together. So therefore, all these 3 factor iteration, I will group them, become the sum of square for error. This one is if you have an experience about you do not want the 3 factor iteration. Okay, if you do not have any idea of this thing, then we will go toward the second option. If you do not have anything, then we can be plot the normal probability plot here. So when you're doing plotting the normal probability plot for all the effects, by right you have altogether is 15 effects, but you must remember ABCD is together already with the block, so that therefore you can't estimate the sum of square for ABCD anymore. So excluding the ABCD, you only have 14 effects. So you're plotting the 14 effects, then you can identify which are the important factors to be considered. Okay. So the here important factor will be considered. Then you have a block. Sum of square for a block, they put the bracket here because the ABCD were confounded together here. Then your error, the remaining of them not important one, they will put it as an error, the sum of square for error. Okay, so they do the grouping of all these things. So as you can observe it, sum of square for ABCD, you do not have it because they already confounded with the blocks. Okay, so this is this one is what I have discussed with you all. Okay. So after that, I also discussed instead of doing the confounding of the 2 blocks, you also can go up until the 4 blocks, 8 blocks, and so on. Okay, so it's an example for confounding with the 4 blocks. Okay, they put it in the 4 blocks. So when you do the confounding for the 4 blocks, the information lost will be you need to find 2 factors to be confounded. So the suggested in this example will be ADE and the BCE. They do the confounding, and then when you do the confounding of the blocks, the iteration of these 2 confounded blocks also is one of the information were lost. So how to get the third one here? You just ADE multiply by the ACE. So therefore, you can see that the E will be squared. So what you E squared will equal to the 1. Okay, you can write it as a E squared equal to 1. So it's a nothing. Or you can put it as a I. I is like the identity here. So that is a ABCD. So there are 3 factors to be confounded. So therefore, you will lose 3 information from here. Okay, ADE, BCE, BCE, and the ABCD. So 3 information were lost. Okay, so you study is a block here. So therefore, you will lost 3 information. 4 blocks. Okay. So I show you the example of about if you have 5 blocks, what are the blocks is confounded, what are the information were lost. So these are the examples for you have a 3 factor, 4 factor, 5, and so on. Okay, you can recall back what I have mentioned to you in the previous class. Okay, so the following one will be if you're doing the confounding previously, you will lost the information. Okay, for example, just now you have this one. If you divide it into the 4 blocks, you will lost the information from the ADE, BCE, and the ABCD. These are the factors you will lost information. Okay, but you also can be obtain this information if you repeat your experiment. Means that your replication is more than 1. So you can get the information from the other sources. Okay, so that one is called the what they have called as a partial confounding. Okay, so for the partial confounding one, if we do the replicates, we have a then we can estimate the error, and then from there also we can get the information for the other confounding box. Okay, so how to do that? So the first one, I will also begin with the same statement. Unless the experimenter have a prior estimate of the error or willing to assume the certain iteration to be negligible, they must be replicate the design to obtain an error of an estimate of the error. This one will be starting with the factorial design. You also know that your n must be greater than 1. Okay, if your n is equal to 1, you are unable to calculate your sum or square for the error. So if the n is equal to 1, the sum of square will equal to 0. So that therefore you can't get this thing. Then you need to do is combine those of the high order iteration. Okay, but when you combine the high order iteration, you may lead you to the different results, because some of you may be combine if let's say we are studying about the 4 factor, you'll combine the 4 factors iteration to the sum of square, or you combine the 3 factor iteration to the sum of square. So all these things will lead you to the different results. Another option is we are doing the plotting of the normal probability plot. Directly we can identify which are the important factors. So we go through this one is the last one under the G chapter is called the partial confounding. So the idea of the partial confounding is say I give you the following example. Say there are 3 replicates with 3 effects have been confounded in each of the replicate. Okay, we have 3 replicate right now. So this design is said to be partially confounded. Means that for the first replicate, we do the confounded with the factor A. For the replicate 2, we do the confounding. The B will be confounded. For the replicate 3, confounded. So therefore, you can see that the 1 and the B were together because they're under the same sign. Under the A were confounded. So if you repeat for the first replicate, you have do the A, B, and the third replicate is AB confounded. So in this case, how are we going to get the information of the A? If you do the confounding of the A, you do the confounding for the B and the AB. So all these factors have been confounded. So therefore, you cannot get the information. But you can get the information of if you do the replicate of here. If it's confounded here, you unable to get the A factor A from the replicate 1. But you can get the information of the A from the replicate 2 and the 3. Okay. Similarly, for the factor B, for the replicate 2, you are unable to get your sum or square for the B. Okay, but you can get it from the information replicate 1 and replicate 3. Okay, the last one is the AB. You unable to get your sum or square for AB from the replicate 3, but you can get it from the replicate 1 and replicate 2. So this one is called the partially confounded, where you can get your information from the others replicates. Okay. So here, as I mentioned here, okay. Okay, if you I think I missed out the table here. Okay. Okay, this one is one of the example here. I think okay. So here, as a result here, I think this one is just a one example here. Is I show you just a two replicate here. I think I miss out the table of here. I miss out the table of here. This one is that's all for the first section. Okay, for this part will be that's all. So now the bottom here is actually you consist of the replicate 1. Then you have a replicate 2. You have a replicate. You have 4 replicate here, where replicate we do is ABC. Okay. For the second one will be the AB. This one will be BC. This one will be AC. Okay, so we have all these factors where we do the confounding. We have all together will be the 4 factors here. Okay, so you all together you have all together is a the replicate 1, 2, 3, 4. So if you have 4 factors here, you have a 4 confounded here, ABC, BC, and AC. So since you have all the 4 different of the confounding, so here is what is I mentioned here. As a result, information from ABC can be obtained from the data in the replicate 2, 3, 4. You can get from the 2, 3, 4 here. For the information of AB, for the second one, you are unable to get, but you can get from replicate 1, 3, and 4. For the third one is the BC, you can get from the 1, 2, 4. The BC is confounded here, you can get from 1, 2, 4. Finally, AC, the last one is you confounded, but you can get information from replicate 1, 2, 3. Okay. So through this way, where you can get all your all the confounded factors, means that all the sum or square for the ABC, AB, BC, AC, all you can get it out. Okay, and then some more you have a replication. You also no need to combine your sum or square. You can have a sum or square for error. Okay. So in this one is the example will be show you here. Okay. So what are the factors we have here? Okay, we have a sum of square for the replicate. Okay, you can have a sum of square for the replicate if you only have a 3 factors here. Okay, if you have only have a 3 factors here. Okay, so we have a sum of square for the the sum of replicates, and then we also can have a sum of square for the blocks. But the blocks itself, they will consist of the ABC, because you have confounded with the replicate one, AB, BC, and the AC. So therefore, all these ABC, AB, BC, and AC, you are unable to obtain. Okay. However, you can be get their sum of square is because you are do the confounded separately, partially confounded. Therefore, the AB can be get from the number replicate 1, 3, and 4, and the rest of them will be similarly. Okay. So we have a the sum of square for the here is A, B, and the C here. Because this example is just show you is just a 3 factors here. We only have because it's 2 power of 3, so it's a 2 power of k. Okay, where the k is equal to 3. Only 3 factor case. So therefore, we can list down the A, B, C. You have a AB, you have a AC, you have BC, you have ABC. Okay, so altogether is 2 power of 3 is 8. 8 minus 1 is a 7. So have 1, 2, 3, 4, 5, 6, 7. You have all the 7s, the factors here. Okay, what we say the main factors and the 2 factor iteration and 3 factor iterations. Okay, all of them you can obtain. If you're doing the replicates, then you can get the sum of square for error. Okay, and then you have a block itself, because in this case you consist of the Nelson factors, so therefore you have a block here. Okay, so this one is one of them is called the partially confounding. So under the partially confounding, I will give you the example of here. If we study about the 3 factor case, we have a factor A, B, and then we have a factor C. So we want to study for the three factors here. So only the 4 treatment combination can be tested during a shift. You only can test each time 4 treatment combination. So you have this one is 3 factors here is a 2 power of 3 is equal to 8. You have a 8 treatment the 8 of here, the 2 power of 3 here. You have an 8 treatment combination here, but each times only during a shift only have a 4 treatment combination you run. Okay, and then because there could be shift to shift differences in the etching tool's performance, so the experimenters decide to use a shift as a blocking factors. So if your experiment you do not think that the shift they have a different shift have any factor or the shift as one of the Nelson factor to affect your results, then we no need to consider the blocking. We no need to consider the confounding. Okay. So because this experiment, they think that the shift will affect their results, but the shift is not their main factor. It's just the Nelson factors. Okay. So therefore, they need to use but when they run the blocking, they are unable to run all the treatment combination within a block. They only able to run 4 treatment combination within the block. Therefore, they have for the first block, they consist of the 4 treatment combination. Another block, they consist of another here treatment combination. They have a block 1 and they have a block 2. So for the block 1, they only consist of 4. This one also 4. Okay, so they have a 4 treatment combination. They have a 4 treatment combination. Okay, so this one is what you have here. And then because the experiment, they can replicate it. They can repeat the experiment here. Okay, each replicate of 2 power 3 must be run in the 2 blocks. Then 2 replicates are run. with the ABC will be ABC will confounded the first one, and then the AB will confounded for the second one. So they run it separately, then they do the conf. Okay. So in this case, where you have a different confounding here, the replicate one, you will get your ABC. Replicate 2, you will get your BC. So these are the experiment they run it out. Okay. So the experiment they run it out is these are the data set they obtain. Okay. So you can be checked if you want to check the ABC. You can be checked all the negative sign or the positive sign were together. All the negative sign will be here. All similarly for the AB confounded, all the negative sign will be here. All the positive sign will be here. Okay. So we can be calculate from the experiment here. We can calculate the sum of square. From the sum of square for the A, of course, you can calculate it out. You can be calculate the sum of square for the B. You can calculate the sum of square for the C because you have a replication. When you calculate the sum of square for the A, you need to merge it out together. Later, I'll show you an example. So the sum of square for these three, you can get it. Similarly, you can get the sum of square for the AB. You are unable to do it because you are confounded here. So you only can get the sum of square for the BC. Okay, then you can get your sum of square for the AC. This one is what you can have. Okay, so altogether you have altogether is a 7 sum of square. So here have a 5 sum of square. You have another one is a sum of square for the block. Okay, because you have a blocking here, therefore you have a sum of square for block. For the sum of square for the ABC, okay, you are unable to get from here. You can be get it from the replicate number 2. Therefore, the ABC you can get it also. Then the sum of square for the AB, you unable to get from the second replicate, but you can get it from the first replicate because they are not confounding the AB. Therefore, they can get from here. So you have you get it from the 1. Okay. So altogether, the sum of square 1, 2, 3, 4, 5, 6, 7, 8, all the sum of square you can get. And then because this experiment, they have a replicate. Okay, they have a replicate. Of course, you can have a sum of square for the replicate if you wish to have the sum of square because you repeat your experiment. And then some more, you have a replication. Then of course you have a sum of square for the error because you repeat your experiment for twice. You repeat it out for the 2 replicates. So therefore, you directly can be get the sum of square for the error. So these are all the sum of square altogether is a 2, 4, 6, 8, 10. 10 of them. Here 3, 6, 7, 8, 9, 10. Okay. So when you want to formulate the ANOVA table, you need to know how the sum of square will be obtained. Okay. So you to get the total, you will get your sum of square for the total finally. Okay. So to get your sum of square for the replicate, sum of square for ABCD or the ABC and the ABCAC, all these things. Okay. So I will give you the example if we want to calculate the sum of square for the A. Okay. Let me see. Okay. Here is a ABC. Okay. So okay, I show you this thing first. For example, if you want to get the sum of square for the A, if you we want to get the sum of square for the ABC first, then and the AB first. Then after that, I will show you the other sum of square here. Okay. So in this example, if you want to get the sum of square for the ABC, how are we going to get? As I mentioned here, in here, I will say that the sum of square for ABC is get from the replicate number 2 here. ABC will get from the replicate number 2 here. So means that I'm using the data here to calculate the sum of square for the ABC number 2. So how I do it? Okay. So I will do it here. Later on, you can see the working at the bottom. Okay. So to get the sum of square for the, actually it will be the same. If you want to get the sum of square, okay, I will get from the replicate number 2. Okay, so this is a replicate number 2. So if you want to get the sum of square, if you still remember, the formula will be equal to the contrast of the AB C square divided by the number of the here is the n times the 2 power of k. Okay, if you still remember what you have learned it before, this one is what you have a formula here is a contrast square. So now we use the data from here to form the contrast of the ABC. But bear in mind that this when you do the grouping of here, the grouping of here ABC, this type of the grouping, you grouping the minus sign and the plus sign together is according to the AB minus sign and the plus sign. Okay, but you want to calculate the sum of square for ABC, you get number 2, it means that you need the data, but your arrangement of the contrast, you must be according to the ABC, which one is a plus, which one is negative. So therefore, here they have arranged it according to the ABC. Okay, they already arranged according to ABC. Therefore, my contrast here will be the data I get from the replicate number 2. But the arrangement of the contrast, I will using the arrangement. Since here you have it. Okay, so the sum of square for the ABC, the plus sign will be the A plus, because the plus here, B plus C plus ABC. Then this one is a minus 1 minus AB minus AC minus BC square divided by n, because inside here you only have a one observation here. Then it's a 2 power of k. You have a 2 power of 3. Okay, so now because I say that the ABC get from the second replicate, so the data of the A will be 650 plus the B will be equal to 601 plus the C, the data will be 1052 and plus so on until the last one negative BC will be negative 1063 square. Okay, divided by the 8. So therefore, you will get your sum of square ABC from the second replicate will be 6.125. Okay, so this one is about your sum of square. You get partially from the replicate number 2. So the working here is actually from here. It's similar to what I have shown it to you here. Okay, it's ABC minus ABC plus ABC minus 1 and so on. Okay, but you can see the data is get from the elsewhere. Okay. Similarly, if you want to do for the sum of square for the AB, you get from the replicate 1. Okay, so means that you need to get from the replicate 1, but you need to get the sum of square for the sum of square for the AB. The data is come out from the data number 1, so you need to have a contrast for the AB square divided by n times 2 power of k. Okay, so you need to get the contrast from the contrast here. Okay, you need to get the contrast of the AB, but the here show you already the contrast of AB. So therefore, you have here will equal to the 1. Okay, the second cell will be equal to C. Okay, you will get your AB here. Okay, the sign of the AB here. Okay, so you will get your 1 here, and then the C, AB, and the ABC, and then the other one will be the A, B, AC, and the BC here. Okay, so you get from the here, and then you get from the here. Okay, so this one will be equal to,
Sorry, doctor. I want
yeah.
to ask for AB, shouldn't we use the data from replicate 1 instead of replicate 2?
Yes, the AB, we need to get the replicate. The replicate is come from the 1, correct? It's you need to use the data from 1. But how are you want to form the contrast? because here have arranged it for you. So therefore, I will use the 1, C, AB, and AC. Okay, okay, maybe this one, you can see here, AB, as sum of square for ABC is you can't get from here. You can be get from the replicate tool. So therefore, the data is get from the replicate tool. But the arrangement of the contrast, because here already show you the arrangement of the contrast ABC. So therefore, I will arrange the data according here. But I arrange the treatment combination is according to here. But the data, I get it from here. Therefore, you can see that the first cell will be 650A, then the B will be 601. So similarly for the AB, get from the replicate 1. Okay? Huh? For the AB, you can't get from here. The data you must use here. But the arrangement of the contrast, you can be arranged according to here. Okay? It's a 1, C, AB, AC. Okay? 1, you can see 1, AB, 1, C, AB, sorry. Oh, wait, 1, C, 1. After that, you have AB, AB here, and then after that you have a C, and then another one is a ABC. So these 4, you can see that in this one will be the 1 is a positive sign, 1 ABC, and then C and the AB here. These 4 will be together, these 4 will be together. But the data set itself, AB, you need to get the data from the number 1. So you can see the is referred to 550. They are not take the 604. Is it clear?
Oh, okay.
Okay. Huh?
Okay.
Yeah.
Yeah.
So this one is why you get your sum of square. Your sum of square for the AB. Okay. You get the sum of square for the AB. Okay. And then this one is what I always use the notation as the sum of square, the bracket number 2 to indicate that you are getting from the others observation. The sum of square get from the other observation. Then you get the sum of square for the 1. You get from the sum of square for other of from the first observation. So therefore, in your ANOVA table, you have the first one and the second one. This you will get these 2 of the sum of square here. And you have another one is here. These 2 is sum of square, you already found. How to get your sum of square for replicate? Okay. You want to find the sum of square for the replicate, then you need to get the sum of square from here. So you can be total out the replicate for the 1. Okay, the total out because you can see the H is equal to 1 until the end here. Okay, so you only have a 2 replicate here. So you have a 2 replicate. So means that from the first replicate, you just total out the total out all the observation square. So divide the observation here. Okay, because you get the total of this one 6084. Okay, this one is a 6084 here. If I refer to this one, you have a first replicate. If you do the counting of here, okay, will be equal to 6084, the total observation here. Similar to here, 604. The total will be 6333. Okay, so this one is a total from the first replicate. This one is a total for the second replicate here. Okay, so the total of the first replicate will be the 6 of the second replicate. Okay, will be 633. Total of the second one is 633 then square. Okay, so you total out here, then you divided by 8. Why you divided by 8? Because for the each total, for the this total, you get the average from the 8. Okay, 8 observation here. So therefore, you divided by 8 here. Okay, so you minus by the grand total square divided by 16. As you can observe it, almost all the formula except the sum of square for error, you need to use the total minus the sum of square of error. Other than that, all the sum of square, they will, okay, means that is using the sum of square divided by n. Okay, so I believe that when we go through the factorial analysis, you can observe it. Sum of square for a. How do you do it? It's the mean for the each one. Square it out divided by number of observation minus the grand total square over n. The sum of square for a, sum of square for b, sum of square for ab, sum of square for the abc, and so on. Almost all of them, they have a similar pattern. Okay, so this one is refer to the second. The third one is about your sum of square for the here. Okay, AC and BC. How are you going to do that? Okay, so you have here. Okay, you have all the observation here. Okay, so if you want to get your sum of square for the A, okay, if you want to get your sum of square for A, what you need to do over here, if you want to get your sum of square for the A here, then you need to get your contrast for the A square. Okay, you need to get your contrast also a number of n times 2 power of k. Okay, so the contrast of A, if you refer back the contrast of A, I do not, let me see, the previous one, you have the plus minus sign. You have a, yeah. If you refer to the above one, I will directly put the contrast here. If you refer plus minus signs for the A, here now, here is the contrast of the A you can get from this parenthesis is a -1 plus A and so on. Okay, so I will write it down for you. Okay, if you want to get this thing, then they should be equal to -1, -1. Okay, it should be this one. It's a -1 plus A minus B and so on square. Okay, why is the n is a 2 here? Because this one is your experiment you run. In the overall one, the one you run for twice. So your number of replicate it should be 2. Okay. So if you want to calculate, of course, you need to put in the -1 here. The one here is not same like the one of the here. Okay, the one here is will be the negative. The one here is means that the total of both. The total of both of them. Because you want to calculate the sum of square for A, you will total up these two, you'll get 550 plus 604. So it's 1154. Okay, so you will get the then plus your A. Okay, the A, the second cell, I just list it now. The A is a 669 plus the A here is a 650. So you get 1319. 1319. Then minus by the rest of them. You square it out. You divide it by 2. Here is 2 power of 3 is a 8. 8 times 2 is a 16. Then you get your sum of square. Okay, so you can be try it out. Then you can get your sum of square for the A. The sum of square for A. The similar works for the B, C, and the A, B, C, and the AC and the BC. Okay, so this type of thing, you need to combine it out. Okay, so you can try it out for this one. Easy, you also can do that. So another thing is because you have a blocking here, you have a blocks. So how many blocks you have right now? You have 2 blocks here. So you need to get your sum or square for the blocks. So how you want to get your sum or square for the block here? Okay, so to calculate the sum or square for a block, the sum or square for the okay, so the sum or square for the blocks here, I can be calculate it out. Okay, so for the first block, wait, wait, I will do it, then I will show it to you. Okay, maybe I will do it later because I need to type it out. So for the sum or square for block, so you have a here, you can observe that you have a block. This one is a block 1, this one is a block number 2. For this fabricate, this one is a block number 1, this one is a block number 2 here. So you need to combine together with the both of the blocks here. You need to combine of the total of the both of the blocks here, and then you get your sum of the blocks for the first one is a square out. Okay, and then you get the second block is square. Okay, so for the sum or square for a block here, you can be using the simulation. Okay, I will write it down for you later on. The sum or square for the block 1 we can get from the first one, and then plus the second one of the block here. Okay, so we have a first one. Actually, they come from the this one, this one, this one, and this one. So the sum or square for the block here, I will show it later on to you. Okay, during the break, I will write it down. Then I will show it to you. Okay. So anyway, the important thing in the part confounding here will be the sum or square for the AB and the ABC we get from the different blocks. Okay, so this one is what you can have in the partially confounding under this example. Okay, so later on I will put it here. I will put. Okay, in fact the values of here they mentioned in the text here. Okay, let me see I put the text for you or not. If I don't put it there, okay, so I will calculate, let you see the form, how do you calculate the 458 here, then I will put it later on, you put it here. Okay, so once you get your all the sum or square, you also can get your sum or square for total. Okay, so after you get the sum or square for total, you minus away the rest of sum or square, then you get your sum or square for error. Okay, then after that, we can be test which factor are considered as important factors, inclusive the ABC and the AB. So if you observe of this value here, okay, we can see that the factor A, if we test our alpha at the 5%, if we test at the type 1 error at the 5%, so we found that the factor A will be important factor. After that, we have a factor C, also is an important factor. Then we have a AC. Okay? The iteration of the A and the C also is important. The rest of them, AB, the P value is 0.29, so it's greater than alpha, so therefore it's not important. ABC also is not the important. So we only can identify these are the three factors are important. So after we identify these three factors are important, then we can use these three factors to form our the regression model. Okay, so we can do the ring and then we can use that particular model to do the prediction. Okay, from the ANOVA table, it just helps you to identify the important factors. So later on, we will put in the models. Okay, but the model, of course, we have a different type of the models, and then we will do the prediction. Okay, so this one is about the parts of the sum of the confounding idea. Okay, the sum of square for a block, in fact, I have calculated it out is here. Okay, the only thing is I don't show the formula here only. I just tell you about this thing. That I will show you about how to get it out, the sum of square there. Okay. So this one is the first for the first case of the partially confounding. Okay, I have some more examples I will give you in the tutorial question. Okay, so as a summary for this chapter, this chapter will be optional if you have the Nelson factors. If your design do not have include any of the Nelson factors, you do not need to consider confounding idea or the blocking idea. Okay, of course, the blocking is a full blocks you run. Confounding, you just run for the partial of the treatment combination. Okay, so this one is the design is under 2 power. Okay. Yeah. So for the other sum of square, as I mentioned later on, I will I write it down. I will put it here. Okay. Then I will upload it. Let you see about the last one of here. Okay. Any of you have a question before I continue? Okay. Okay. So if you do not have any question, for time being, if you do not have any question, then we will proceed with the following one. Okay. So far we have go through the first chapter. The first one is for the single factor. Then after that we introduce the blocking design. Then is followed by the following one is a factorial design where you consider a lot of the iteration components inside your model. Okay, so we have a general factorial design. After that, in the previous chapter, the chapter number 6, we will study is a 2 power of k factorial design. Means that we only consist of every factors consists of only 2 levels. Okay. So after that, we will go through this chapter is a confounding and the blocking and confounding under 2 power k. So after this thing, we have another chapter here. This one is also we study about the 2 levels case. Okay, we also study about the 2 power of k case. Okay, we study about the 2 power of k. Okay, but right now the 2 power of k here, you have a many treatment combination. We are not consider the Nelson factor at all. We only run for the fraction of the 2 power of k. Okay, we run only the fraction of them. Means that if I have a 2 power of 2, I have altogether is a 4 treatment combination. Okay, I only have a 4 treatment combination. I only need to run 2. Okay, half of them, quarter of them. But of course, this one is a 2 power of 2. You are able to run all the treatment combination because it's only 4 treatment combination only. How about if you have a factor 2 power of 8? If you have a 2 power of 8, let's you all together, if you want to run, you have a 250 treatment combination. So you want to run is all together is 256. So if I want to run only part of them or half of them, I still need to run. I divided by 256 divided 2. I will run is a 128 treatment combination. Okay, I only run half of them is a 128. If I want to run only quarter of them, so 256 divided by 4, I have to run 60 combination. Okay, so this one is what we call as the fractional. You are not going to run all of them. You only run partial of them. Either it's a half or the quarter or 1/8 of them. We will expect that when we run only the, let's say half of the treatment combination, we want to, from the half of the combination here, we get the information for all the 8 factors here. Okay, but as I mentioned to you, once you run the last treatment combination or you perform the combining idea, you will lose certain information. Okay, so this one is an idea for the today. It's a two-level fractional factorial design. Okay, so here will be I mentioned is here. As the number of factors in the 2 power of k factorial design increases, the number of runs required for a complete replicate of the design rapidly outgrow the resources of most experimenters. This one is what I mentioned. If you have 8 factors, you all together you need run 256. But if you run it 2 power of 9, then you have some more. You have 2 power of 10, then you have many treatment combinations. Okay, so I give you the example. If you run for the 6 factors under the single replicate, you need to run 64. If you have 64 of them, okay, under the 64 runs of here, you consist of the 6 main effect because you study the 6 factors. So you have 6 of them, and then you have 15 of the 2 factor iteration. Then the remaining one, you have 42 3 factors and higher iteration. So here are the contribute to the rest of them. So total out, you get the 42 plus 15 plus 6. You have a 63 effects. So here, the first thing is just tell you that because our main target of studying the factor is, of course, our main factor will be very important. We want to know that what are the important things of the main effect. Then at the same time, you also need to care about the 2 factor iteration. Because the 2 factor iteration, it means that the factor A will affect the factor B. Okay, when you have a AB is significant, so the factor A will affect the factor. When we go to the 3 factor iteration, of course, we need to study the 3 factors together. But most of the time, we will do the grouping of the 3 factors and the high order iterations together. Because if you study too many of the iteration, then they want to interpret a result is will be very difficult. Okay. So this one will tell you that we have a 6 main effect, 15 and the 42 here. Okay. So if under this case here, if the experiment have a prior information on the second high order iteration and assume that the high order are negligible, then the main effect and the low order iteration may be obtained by running the fraction of the complete factorial. Okay, so this one is meaning that if you are running the 6 factor here, you all together should be run is a 64 treatment combination. But out of this 64 treatment combination, you only need 6 of them to study is a 6 main effect and the 15 of the 2 factor iteration. The rest of them are grouped into the higher 3 factor and higher iteration. Okay, but our target is just about this thing. So under here will tell you that if you can assume something is can be negligible, then we have information to be study only the main effect and the lower effect, lower order here. then we only need to run the fraction of the complete factorial design. Okay, so therefore the major use of the fractional factorial design is a streaming experiment. Means that now I have 10 factors. If I only run for the fraction of them, I can then identify the important factor. Then they will help us to scream out what are the important factors. So this one is here. If you run completely all, then you will take a very long time. If you have 10 factors, then it's a 2 power of 10. So therefore, they need to go through 1024 treatment combination. So we are not do that one. We will just run for the fraction of them. Okay. So if you use a software, I believe that they can run until the 15 factors the fractional factorial design. Okay, if I'm not mistaken, the Minitab, they can go up until 15 factors. So the successfully of use fractional design is based on the three key factors here. Okay, so when there are several variables, the system or the process is likely to be driven primarily by the sum of effect and the low order iteration. Okay, because as I just now mentioned here, you have a 6 factor here. Most of the time, only the main factors and the 2 factor will be contribute or will be affect the result. The rest of them is normally they are not significant. Okay, most of the time 3 factor and on they are not significant. So therefore, when we study the factorial design, we are care about the main factor and the 2 factor iteration. Of course, if you want to maintain the 3 factors also, you can be checking out. If you have many of the iteration, you also can maintain the 3 factor. But you can see that 4 factor iteration, 5 factor iteration, all the factor iteration, they may not be significant. Their contribution very okay. So the key point here is say that the system will likely driven by the mean effect and the low iteration. Okay. The second one, the fractional design here can be projected into the stronger design in the subset of the significant factor. Means that you only run the certain fraction of the design, then you can be identified those of the significant factor through this style of design. Therefore, you can project in the stronger design. Means that if let's say I have a 6 factor analysis, so we can identify only the 2 important factors. So our 6 factor case, we can reduce into the 2 factors design where they consist of the 2 factors and if the operation. Okay. So this one will they can projection properties. They can be from the very high order. They can reduce it to the certain factors only. Okay. The following one, it is possible to combine the runs of the 2 fractional design to assembly the sequentially a larger design to estimate the factor effect and the interaction of the interest. Because for example, you will run the 6 factor factorial design. You only run the fraction of them, maybe half of them. Then another design, you also run the half of them. Then you combine together, you can be estimate all the effects. Okay, and the iteration of the interest. So this one is what are the key points of the risk rate. The main thing of the fractional design is we do not want to run all the treatment combination. So we only able to run the part. Then we run the fractional design. So we expect that based on this fractional design, we can be identify the important factors. Okay, so later on, I will show you the examples of the how is it the fractional design where they can be see that you run the full factorial design and then you run the half of the 1/2 of the fraction of the design, then you can get the same information. Okay, so now we go through this one first. We still have a time. Okay, the 1/2 fractional of the 2 power of k design. So if we only run the 1/2, then we use the notation 2 power of k minus 1. Okay, I give you an example here. if you have here, if you have three factors with two levels each, so because we are studying the two levels, and then we have a three factor, therefore we put as a two. We have all together is a 8 treatment combination. We all together we have 8 of them. Okay, so if we want only run the 1/2, so we will use a notation as a 2 power of 3 minus 1. You will get your answer is equal to 4. So means that suppose we have a 8 treatment combination, we only need to run 4 of them because you want to run 1/2. Okay, so they only have a 4 runs in the 2 power of 3 design. Okay, so when you want to run for the only 4 of them, okay, if you recall back what you have learned before in the blocking and confounding, you need to have a confounding of here. Okay, so in the fractional design also, we need to something to do the divided them into the only run for the 4 of them. Okay, so how we want to know which 4 of them to be run? First thing we need to know what is meaning by what they call as a generator. So the first one is called the ABC. I give you an example first. ABC is the generator of the design. They call as a generator, or they use a name as a words. Okay. So the higher orders iteration, they will use as a generator. Okay, similar to what you have learned in your confounding idea. The highest order, you will use the factor to be confounded with the block. Okay, so this one is we divided into the half first. Then we have a first definition is called the here the generator. We use the ABC as a generator. Okay, the first thing. The second thing is by selecting only those of the treatment combination that have a plus or minus signs in the column ABC. So because you run only the 4 here, means that you can be from this diagram here. These are the treatment combination. We have it here, okay, from the A until the here. So we list down all the plus minus sign here for the factor A, B, C. Okay, we write in the following one. Okay, of course, this one is not ordered according to the standard order here. If I mention the standard order, we will write the 1, then followed by AB, then followed by AB, and so on. That one is standard order. But this table they arrange in the following one is because they want to let you know that we are doing for the user ABC as a generator. Okay, so the plus minus sign, all these things, I believe that you can be working out. Then even though the ABC, they also can get it out. Okay, so in the fractional factor design, they either will run all the positive will group together, all the negative will group it together, because you use your generator as the ABC. So therefore, we will use the ABC to do the grouping. The idea is similar to what you have done in the confounding. You group all the signs together in the same block. Another one is in the other block. So the idea here also the same thing. You group, if you use the ABC as a generator, then you do the grouping of the all the positive sign together, all the negative sign together. Combination here, and you have another treatment combination. Okay, so you have a 2 treatment combination here because under the 2 power of the k minus 1 fractional factor design, you only plan to run 4 runs. You all together have 8. So here, run all the 8 treatment combination means that you are running the 2 power of k factorial design. But now we only want to run only the part of them. Either you run the first one or you run the second one. Okay, so this one is called the fraction of them. You only run the ABC, ABC, or you run the AB, AC, BC, and 1. Okay, you can choose either one of them. If you choose the first one, then the notation will be plus. The sign will be plus. If you choose the second one, then the sign will be negative. So we will expect that we want to study is a 3-factor factorial design. We have so many factors to be considered. We will expect that if we running only these 4, we will get all the information of here. We want after we run these 4, we want to know that okay, which factor are important. We will know. But of course, we need to give out something information. Then we only can identify which are the important factors. You are able to run all the treatment combinations, you can be run all. But as the number of factors increases, then you need to run many treatment combinations. That one is very time consuming. Therefore, we only run the of them. Okay, so here I list down in the form here. Okay, where you have just now the A, B, C, A, B, C, A, B, C. These are the A, B, C, A, B, C. And these four treatment combination. Okay, so the here is called the principal fraction. So because you still remember you have a generator is a ABC, and then because the sign is a plus here, then we can return it as a I is equal to plus ABC. Okay, the sign is a plus because you are grouping of the all positive sign here together. If you run for the another set of treatment combination, if you want to list down in the following one, three factors here, then you run the one, you run the AB, you run the AC, and then you run the BC. So this one, we put it as a I will equal to negative ABC. Okay, they put the negative here is because you are running those of the negative side. So that one is a called. You also can run here. So out of these two treatment combination, you only run one. Okay, so the name for this one, they will call the principal fraction. If you run another one, the negative side, then they call alternate fraction. Okay, so this one is these two here. You have a principal fraction and then you have an alternate fraction. So this one is a diagram for just show it to you that under the three factors, first keywords is a generator, and then you have a plus minus sign here. Okay, so how important is a generator here? Actually, the importance of generator here will lead you to the certain of the factors here. Okay, so we will go through the following one. Okay, I just go through one more here. Okay, so under here, under the fractional, the following definition will be the defining relation. So how we want to find the defining relation will be using the I is equal to ABC because our generator or the words is a ABC. Therefore, we just put it the I is equal to ABC. Okay, there is a meaning of this thing to consider. So the defining relation of the fractional factorial is the set of all columns that are equal to the identity I. Always will be the plus sign here. Okay, so the I is equal to ABC here. Of course, you can be calculate also I equal to negative ABC. They tell you is the other side only. Okay. So from the defining relationship here, okay. So from the plus and minus sign of the table here, we may estimate the main effect of the A, B, C as follows. Okay. So how are we going to estimate the main effect of here? Okay. So this one, I think that we take the break first. Okay. You take the break first, then I will continue with here. I have here, I will list it down for you all. Okay. So I think now we start break first. Then later on we come back around 7:50. Is it possible? Okay. I think we take the break first. Okay. Okay, huh?